measure. And in this case, we're looking at chi-square. And I have this x right here in the -1 because a lot of times when you're dealing with larger larger samples, chi-square is a very sensitive model, and it does detect trivial differences, and it comes back as a very stringent way of saying there's something wrong with the fit of this measure, where it's just one way in which to test the fit of the measure. It's not like all stop, where if you have this assumption being violated right here when it comes to fitness, then you have to stop your approach. There are many other ways in which to test the fit of your measure. There's CFI, this SRMR, which is standard root mean residual, and then you have residual mean. Sorry, let me say that again. So this is SRMR, so this is the standardized root mean square residual, and this is the RMSEA, the root mean square error approximation. And so these are very important metrics of, well, not metrics, but ways, indications of fit. And so even if you have one demerit or one mark off, there's other ways to tell if your measure is fit or not. And in this case, we have CFI, it needs to be at least 0.9 and ideally 0.95. And then you have SRMR, which is less than 0.8, and RMSEA, which is ideally less than 0.06, but it could be less than 0.1 at the bare minimum. And in this case, at this particular research, what they found was their normality assumption was violated, and so what they had to do was do a maximum likelihood robustness standard error. And if your normality is not violated, then you just do a maximum likelihood. And so in this case, they just had to do a slight detour into MLR. But nevertheless, they were able to fulfill their assumptions with the tweak with the MLR and move on to measurement and variance. Now, here's the general flow of measurement and variance. And in this we see, well, this figure right here is a illustration of how before we looked at the overall fit of the measure. And now what we're doing is we're splitting up the data into various populations, subpopulations, I should say. And let's say this is a measure, the overall measure is a measure of depression. We separate them up into their own subpopulation, and we look at the general form in configural invariance here. And then we look at metric invariance. We constrain the loadings. And then in scalar invariance, we constrain the loadings and intercepts. And then we put more constraints on strict invariance. And so what we have here is a nested model with various constraints that are put into it. And think of it like hurdles that you have to cross. And if you pass all these hurdles, then we have measurement and variance, and we can adequately and unbiased, with unbiased, we can compare group differences when it comes to whether it be a self-esteem scale, and in this case, in this example I'm going to use, is a depression scale. So before we even start with step 1, we looked at the overall fit of the model or the measure, and then we go to step 0, and this is called invariant covariances. Now, invariance covariance tests whether the covariance matrix among the item is invariant. To do this, you have to create a multi-group model, and then the variance covariance matrix is constrained among the items to be identical. What we are essentially looking for is, in all of these, is whether there is acceptable foot that's maintained. And there's going to be, like what we said before, or what I said before, is various ways to look at acceptable fit. And I always mark this off as saying chi-square is usually not going to be met because it's just such a sensitive test, but these other fit indices or indicators should be met. The first formal step is going to be configural invariance, and the way that this confirmatory factor analysis is going to look at, or measure is going to look at, is by default we have the loading set at 1 and the intercept set at 0. And this doesn't make sense if we're comparing groups based on how all of these are items with their individual questions. And here's the latent factor, which is depression. we want to compare all these items between all subpopulations, so it wouldn't make sense to set the first one to be 1. Then we wouldn't be able to compare all these items. And so what needs to be done is to remove the default settings, whether you're using SAS or M+, or R, any type or most type of statistical analytical programs is going to set this default setting. And you have to override it by placing the mean as 0 and the variance as 1. That way you can compare all these particular items across all these other subpopulations. And let's say in our simple example here, we're comparing depression scale between an American sample and a New Zealand sample. Now, what we need to do when it comes to measurement and variance is we are basically testing the shape of the factor across the groups, or the shape of the measure across the groups. We're looking at the direction, size, and p-value. And here's one example of how we can do that, where we have 3 groups. We have BW, LW, and WW. And BW has loadings of 0.58, 0.847, and as long as it's at least 0.35, then it's fine. Then it's working properly. And as long as they're all in the same direction, like these are all positive here, these are all positive here, and these are all positive here, or these are all positive here. As long as they're all in the same direction, then that's one part of configural invariance being met. And then we have the size. So what is the size? And so this is kind of like the outlier, which is 0.583, but they're not wildly off, where this is like 0.3 and these are all 0.9s right here. So I think that these are quite sufficient right here, where the direction, size, and as well as the p-value needs to be significant here. Then we have configural variance being met on this one level. The other level of configural variance is by looking at the indicators of fit. And when it comes to configural variance, since we have a large sample, this is going to be one demerit marked off. But let's say we have a CFI of 0.93. That's pretty good. It's not 0.95. We want at least 0.95. If this was a scale between like getting an A and not getting an A, you would score an A if you got at least 90%, at least in most schools that I go to. It's at least 90% is an A. So you got to at least get that benchmark, and 0.93 is pretty darn good. And then you have an SMR of less than 0.08 and then less than 0.06 RMSEA. And so as long as you have these criteria checked off, you are generally good to go, and as well as this criteria right here. And then you can move on to the next set of criteria. And the next set of criteria is metric invariance. And so you deserve the bronze medal if you're able to achieve metric invariance. And basically what we're doing is we are comparing the fit indices or indicators, primarily in a very liberal sense, CFI difference between configural invariance, which we had at 0.93, and metric invariance, which let's say is at 0.92. 0.92 is at least less than 0.01 difference. 925, I should say, less than 0.01 difference. If it was 0.92, then it wouldn't be less than 0.01. And so in that case, we would have a violation. But since it's 0.925, then it is less than 0.01, and we are able to move on and say that metric invariance has been met. And let's go on to the next level of invariance. And in this next level is scalar invariance, and we are constraining the factor loadings and the intercepts. In this case, we're only constraining the factor loadings, but now we have 2 constraints. And we want to see, okay, no matter of whether we have loadings and intercepts constrained, it's going to maintain its fit integrity in comparison to metric invariance. And so it will be less than 0.01. And so as far as I understand, if we have a metric invariance of 0.925, right, and then if we have a scalar invariance of 0.915, then this would not be met. Scalar invariance would not be met. And so you need to have something like 0.92 or something like that, or maybe it will maintain its fit CFI of 0.95. And that would be nice, but usually it's not going to be that.